Okay, so we wanted today to talk about model serving, especially right now that every one of you, I hope so, you have a model or something that's like ready to serve. And we want to talk about that, how you can serve it and what should be the option for serving, like how, like a, so the first question is, okay, what's exactly model serving? So the first part on top is training a model, which is something that you all have done. It's just a small pieces of your project. Probably you all know that. Most of you, if you have done RAG, you didn't even have model training. Like you just have the architect for making a call. If you even have developed a model, probably you notice that that portion of the work has been much lower effort or a smaller amount of time going through that in compared to the rest of your pipeline. Right? So when you have a model training, the idea of the model serving is that, well, you have a user, someone that wants to access that, and you need to have a way to make this possible. Okay, so you technically need to have some sort of like a access way for user to make a call, send the data to your model and get the response back. Now, when we talk about model serving in overall, you technically need three things. Anytime it comes to, you talk about serving, you need three things. You need a model, you need data, and you need an interpreter. Okay. What is an interpreter? You need to think of like, I have a model file loaded, like it could be like a pickle, it could be like a TF-Lite, it could be a PyTorch, like any format that you basically have saved your model, frozen graph. You need a way to load it, right? So if you use Python, for example, you need a Python to load that model. And for that, in order to load the model, you need a Python, you need an environment that has the necessary libraries and so on. If you have a frozen graph, like a neural network, you can load that, you imagine within Python, you have developed a neural network, PyTorch, TensorFlow, doesn't matter. After you saved it, it's a frozen model. Now, you can serve that in C++, in Java, in Sharp, and almost most of these languages. But in order to be able to serve it, you need some sort of loader. You need some package that in that language, in C++, in Sharp, in Go, in Python, that can load that model. So that becomes the interpreter. Okay, so you need an interpreter, you need a model, and you need the input data. With that, you can make an inference. Now, during also, you need to also remember that the types of basic inference that you can do. So you can do batch inference. Batch inference means that data comes, user is not in rush to get the answer back. And maybe they can wait a day, half a day, 1 hour, 20 minutes, then 10 minutes, 1 minute even. It's not a real time. So when the result that your model provides, it's not real time, what you do batch processing. That means you collect series of basically requests. Whenever you have a full batch, then you send it to the model. If you don't have a full batch, your user can wait. If it's a real-time inference, that's not the case. That means for every data point, you need to make a quick, basically, inference. An example of that could be if you ask a question from any of these language models, that's real-time, right? But probably you have seen these days they have an option, kind of like you can select this type of model that's kind of like a scheduled. So you send a request and you get the answer back later. So that becomes like a batch job. So there are a series of metrics when it comes to model serving that you need to remember: latency, throughput, cost. Okay, this are kind of become really important. So up to this point, the metrics that you have, we really basically caring about was model basically metrics. How good is my model, right? And then also you kind of like optimization metric, like when you use certain optimization technique like Adam, I don't know, like an Adam and so on. But now that you have the model and you want to serve it, the types of metrics that you're going to deal with are going to be different. These three, cost, latency, and throughput, are the really important ones. We're going to just talk about those. Whenever you hear the term latency, you always can imagine this diagram. The moment that user send a request and until the moment they get their answer back. That is the definition of latency. So it becomes sending the data and getting the answer back. So you need to account for both space, like receiving the data, your model processing it, sending the data back. Total, that three basically, you can say, for example, 100 milliseconds for sending the data, 200 milliseconds, let's say, for receiving. And let's say here you also have another 100 milliseconds for your model. So that total technically becomes 400 milliseconds for latency. Now, also important, minimal latency is always really important, okay, from a user perspective, if you are doing something as like a real-time inference. Then you have throughput. Throughput on the other end, it's more around about your basically model. How many data points, how many requests at the same time your model can process? Like that means if you make one API call to your model, and within this one API call, can I send 64 data points or can I send 32? That becomes the throughput, how many data points your model can respond in one basically request. Now, then you also have cost, okay? And the cost basically comes around like, well, what do we need to serve this model? Like, for example, you need cloud infrastructure. You need to account for all those costs. You need accelerators, CPU, GPUs, or whatever you need for it. Even if you do some sort of like a edge deployment, the cost is still around like what you're sending to the customer, and overall basically the maintenance of the, the data comes out of the model, goes to some cloud. Still the data, the model might be on the customer, but there's a cost around how you get the data, how you receive the data, how you process the data. So that's the overall cost. So you need to account always like how much is the cost of this model. And these three metrics, cost, latency, throughput, they could be easily like a break or go with a product. You might have something, but because one of these three is really high, like not two of them is really high, one of them is low, like the throughput is low, and you decided that we are not going to go with this one, right? So it's really important. The idea is that you want to have a balance between throughput, latency, and the overall cost of the model serving. So overall, your goal should be that to aim for minimizing the latency. It doesn't matter if it's actually real time or if it's like a batch. Having a model that in general is basically fast is good. So it's having a minimizing the latency is pretty good. If you deal, for example, for airline recommendation service, if you think about it, you want something to be fast. When you go to buy a ticket, you're searching right now. You're not coming back tomorrow to get the price. So you want something to be fast. But if you now think about it, maximizing the throughput, that means if the traffic is high, your model should be able to answer. If you all of a sudden, so especially if you think, for example, for airlines during the peak time, like a spring break, everyone wants to buy a ticket. End of the semester, most of you wants to go on vacation, buying a ticket. So the airlines will have lots of requests coming through, right? So the model needs to be able to also basically to respond to that the amount of basically requests that comes through. So you want a model that's fast enough because everyone wants the price right now, but also if there's lots of user comes at the same time, your model should be also still respond. Now, your goal will be overall to just again balance between these two. Try to basically do a series of things. For example, you can reduce the cost of the GPU by doing something like GPU sharding, or basically share the GPU if it's not necessary. Like if you're not using it right now, maybe someone else can use it. You can do multi-model serving. You can do certain types of optimization to make your basically inference less costly. We're going to talk about those. Now, so next thing we're going to talk about the resources that is required for the model serving. But first, let's start with the concept of model complexity. So probably all agree with this. The more complex the model, the more expensive it becomes, right? So it's like the higher the complexity, the larger the model becomes, and then you technically need you have a need for a better or more, a stronger, faster, basically accelerator to serve that model. So that automatically increases the cost. On the other end, when the models are larger, the more complex, the latency also increases. Means the model becomes slower. But we also know that the prediction accuracy goes up. Right? So you know, if I make my model more complex, I get a better accuracy, but it becomes slower, and the cost goes up. So it's kind of like we have that idea. Now, when the model complexity goes up, well, you need something like GPU, TPU. You need some sort of like a model registry cost that you have like for saving this model, especially larger models. And the more complex the model, the higher the maintenance, right? So it's kind of like becomes more difficult. And your goal is to basically find some sort of like a balance between all of this. Now, when it comes to metrics that you need to aim for, you technically have two types of metrics. You have model optimizing metrics, again, as we talked about before, and now you have basically gating metrics. And gating metrics is basically latency, model size, GPU load. These all become gating metrics. So optimizing metrics is anything about the model. How good is this model? Gating metrics is anything about like serving the model, how much basically load this model, how hard is to serve this model, how slow is this model, and that overall gives you an idea of like how costly is this model. Now, when you try to optimize for these two, it's kind of also similar to everything else. It's kind of like a loop. It's an iterative process. So maybe at first you're like, okay, we're going to have, because it's not like at first you exactly know what infrastructure you need or what you need for a model. So you come up with an idea like, okay, we are going to use this certain types of GPU, for example. And then because you have that GPU, you have some idea like, okay, we're going to use, I don't know, T100. And based on that, you're like, okay, so we can serve up to this types of basically model. So you maybe increase your model capacity or complexity because you know what infrastructure you have. Based on that, your model performance goes up, like an accuracy perspective, but then also, the amount of basically the gating metrics becomes a bit worse. Now, if the gating metrics is good, then you're good. Otherwise, this loop continues. You go back, you either change your model or you change your basically infrastructure and so on. You need to overall work on this until you get to the point that you're like, we are good. We have a model that is accurate enough. We have a good infrastructure that can serve it. It's not that costly. And overall, when we are looking at our gating metrics, they are basically acceptable. If you have that, then you are good. Otherwise, again, this becomes some sort of loop. So what does that mean is that when you want to build something like for a model, don't think from beginning you exactly should know what infrastructure I need for this, what like a model type I need to have. It's kind of like an iterative process, but having a place to start, especially for infrastructure, gives you some idea about what I can aim to develop for. If from get-go you are told that you cannot have GPU, then I already know that, okay, what types of model I should not go towards. Right? So having that initial knowledge is pretty useful. Now, when it comes to accelerators, there's some stuff to remember is that when it comes to GPU and model, GPU is for parallel processing, right? So when you increase your GPU power, technically you're increasing the throughput concept. Like how many parallel requests that basically I can serve. When you work with TPUs on the other end, TPUs are more useful when you have a larger model that you need to break them down. And you want to basically chunk it, and every chunk sits on some TPUs. So just having more GPU, larger GPU, doesn't make your model technically faster. It's just better for parallel processing. You can have more requests, just something to keep in mind. When you increase those, well, of course, the cost goes up, the cost of accelerators. You need to definitely do some balancing here. And as some sort of like a rule of thumb, if you're new in an organization, don't make that decision yourself about what. Just gather the details that you have about GPUs, types of GPUs, overall costs. Don't go to a meeting like without the information. Just gather some information, go to whoever is your lead, your boss or manager, or maybe it's yourself, and say that, hey, these are the options that we have. Because normally projects have a budget and it's someone in the company is aware of the budget that wants to go towards. Based on that, you can decide what level of accelerator or what type of accelerator we want to use. So also let's make one example here. So imagine you have a GPU and this GPU is like $100 an hour. And what you do, you're like, okay, I'm going to make this GPU stronger. So you go rent another GPU that's like a $200 an hour. At the end, with having a larger GPU, what you can do, you can respond to more requests, right? But that doesn't make your process faster. And you still, even if your GPU can answer for 200 requests, maybe your bandwidth, or an overall pipeline cannot send 200 requests. You know, you have series of things to account for. It's not just the GPU to become larger. Maybe with that, instead of having a GPU that is 200, you could rent 100 GPUs, and you could basically have 2 separate models that are responding the same thing, right? So you need to figure out the balance, see that which one can actually be beneficial for you, having maybe 2 of the same, or maybe if I increase it, I'll just keep that in mind. So the other thing is that like a feature lookup. So whenever you try to optimize your serving, think about feature lookup. So we have talked about this before. Series of features, they don't need to be real time. Like they don't need to be calculated right away. You can pre-compute series of things, and when there's a request, you can just basically refer to those features and just use them during the inference. That can speed up your process. So just keep that in mind, and that different types of data set tables we can basically use for this. We're going to talk about now. There are here we have this. So these are NoSQL basically databases, Google Cloud Memory Store, Google File Store, Bigtable, Amazon MongoDB. These are all good, basically fast databases that you can read, especially as a feature store. That means if you need some sort of like basically cache memory that you can quickly read, it's not for you to do any transformation. It's kind of like a pre-computed values that you can quickly read. These tables are pretty useful, these types of basically databases. The challenge with all of this, in case if probably some of you have done this in your projects, they're pretty expensive, right? These types of basically databases, they are pretty expensive. So unless you actually need it, don't go towards it because they're actually pretty expensive. So now when it comes to deployment, you technically have 2 options. You either basically deploy your model on some sort of like a cloud infrastructure. GPUs are either shared or GPUs you can basically rent exactly for your company and you have your own GPUs. Or you deploy to edge devices, which is like embedded. So you don't need a cloud infrastructure. So if you work with the cloud infrastructure, of course, you know, model efficiency basically. When you rent GPUs, you can have a larger models, you know, have a more accurate. Overall, the cost also is much higher because you know, it's kind of like you renting out GPUs or TPUs or some infrastructures. When you work with on like a mobile deployment, for example, one of the things that you need to remember is that like average GPU on mobiles are 4 gigabytes. Okay, so whatever model you use, like even if it's like a quantized or small version, you need to account that a phone could have 4 gigabytes of GPU, right? And a phone is not only built for your app. There are other apps on that phone that also want to use that GPU. So you need to be sure that whatever app or model basically you have, it doesn't basically take all 4 gigabytes. It should be a small portion of that. Otherwise, you know, a user will remove your app. The other thing is that basically app size, overall, again, it says here on Android, average app size is 11 megabytes. But anytime if you want to download an app, for example, on iTunes, basically it tells you, it's like what's the size? If the app is too large, most of the time you don't even download it. You're like, okay, yeah, no, it's like too large, right? So just keep that in mind. So the larger the model that you have, automatically requires more GPUs. The size of the model, the size of your app becomes larger also. So it's like this too could be a potential breakpoint for user to not download your app. So now, in general, basically, when we work with constraints environment, you cannot work with large models. It's like there are certain types of model you can use, but certain types of model you cannot. If in case you are interested in sending like LLMs to mobile and stuff like that, there is a different category. It's not LLM, it's called SLM, small language models. That they work pretty good on the mobile. So in case any of you is interested to do that, search about SLMs. One of the famous one is 5 models by, I think it's by Microsoft. Those are like a pretty standard, and you can basically deploy it in most of the cell phones. Okay, and I think the new Gamma model also, the quantized version is like a SLM, so you can basically use those. And also, yeah, so if you, accuracy is pretty important, and in real time, like self-driving car, you cannot account for having a cloud infrastructure. It should be right at the edge. So now, well, prediction latency, most of the time is always important, even if you are not doing basically real time. If you do real time, you need to keep one thing in mind. Your prediction latency should be in milliseconds. You cannot basically have a seconds, something like that. Like when I was working in cybersecurity, events are real time, and it's kind of like happens right now. You cannot have a model that takes a couple of seconds, because if something happened right now, you need to block it right now. You cannot just have time. You don't have that freedom, right? So whatever model you pick, that milliseconds for us was really important when we wanted to decide between models to see which one goes to production. One of the main metrics we had was the time, like how long it takes per request to respond. So if we had a model that maybe it was certain basically percentage better than the other one, but it was almost like a 2x slower than the other one, then we might go with the other model, because maybe it's more important for us to have something right away. And what we could do is that we have a second model that could correct the first model, so that becomes a way to have a fast basically response. Now, the other thing here is that, and I think actually this is kind of like a similar idea. So instead of having one large model, you will technically have series of models. So like this idea of like you have series of smaller models, and you will have, so think about here in this image, what you see here, the mobile net, and then we have mobile nets, like a series of this mobile net, and they're like kind of like a distilled for different tasks. So you have a mobile net on your machine that does object detection. You have a mobile net that does face attribute. When, for example, on your cell phone, if you think, when you look at the image folders, like photos, sorry, it already has, based on the faces, categorized images for you, right? So does all of those goes from one model? No. So on your cell phone, there are different image classification models. And what will happen here, you have one classifier, kind of like intent detection, that it basically, when there is an image, when there's a new photo comes to your app, this intent classifier comes up and decides, okay, where this image should go. Should it go to face detection? Should it go to, I don't know, object detection, and so on? So basically, you have series of smaller image classifiers. Instead of having one large, you just basically have series of, I think we can call it also like a mixture of experts. Just they all have, they're doing different things. Now, in general, if you want to basically optimize your model, there are different ways also that you can do that. It's not just having a better accelerator or basically have a mixture of models. But you can also basically try to have some sort of like a benchmarking and profiling to see that if the model is overall basically good. You can optimize for the operators that being used in your model. You can basically optimize for a model. You can tweak the threads that you have. Let me see if we have a slides to break this down, or should we break them down here? No, we don't. Okay, so let's understand what's the meaning of this. So profiling and benchmarking, you always could have some models that you compare your model against from gating metric perspective, from accuracy perspective. If you're comparable with this model, then you can go to production. Otherwise, no. That could be a benchmarking. For optimizing for operators, when you if you work with neural networks and you have built layers and stack all these layers after each other, one thing you can do, and this exists on PyTorch, TensorFlow, all of those they have. There is a way for you to basically run some sort of like a profiling over entire model and per layer, right? So there are different profilers. Again, all these different libraries they have. Even Intel has a profiler that you can use on your model. NVIDIA has a profiler that you can use on your model. And when you run that, those profilers basically tell you that, well, for data came through and went through these layers, and per layer, how much load on memory, time, CPU usage, basically, you have per layer within the model. And what you could do is that if you notice that there are certain layers in your model that are the cause for the slowdown, right? What you can do is that optimize the operator. Instead of maybe using that layer, come up with an alternative approach for optimizing. So the idea would be that just try to figure out what operation within your model causing this slowdown, and try maybe to find a way for that. Or you could basically, if there are certain layers in your model that are causing a slowdown, you could quantize maybe those ones to make the weights much smaller, not the rest of the models, maybe only that one, target them, or do some pruning over there. So you can basically do some sort of optimization for certain parts of your model only, okay? And the model optimization overall could be what you can do on the model. Like if I quantize the entire model, if I prune the entire model, if you do distillation, not knowledge distillation, you basically make the entire model to be more optimized, be faster. And the last one is the tweak threads. And this is the idea, like, okay, I have a model. Now here you focus on how you're going to serve the model. Like you work on infrastructure, or like how you do maybe multi-threading or basically how you do multi-processing for serving your model. So this all become additional ways that you can, after you have a model, you can make the serving faster or more optimized. So now the next thing comes, okay, you have a model and your goal is to serve it. Well, I'm sure for your project, you all have some sort of like a front end and you have some back end. So normally the front end basically it's some sort of like a web page that user can go interact with, and through that front end basically you receive a request from user or query, and you send that query to your backend, and your backend is some sort of like an API also. Now there are different ways, different types of API to use. It's kinda better if for the front end you do something not maybe Python. It's kind of like more like a TypeScript and stuff like that. That's kind of like, it was more flexible overall. Your backend doesn't matter. You can use Flask, Fast API and stuff like that in the backend, but the front end part, you might be better if we don't use Python basically on the front end. Okay, not that it doesn't work. It works, but just it might be better. Now, there are some, what we're going to see right now, there are some libraries that they make this model serving or deployment easier. So they are like, they have some sort of like out of the box, basically, out of the box infrastructure and out of the box, basically, libraries for you to serve your model without you kind of writing much. One of them is called Clipper. So Clipper basically is something like some open source library. I think it was by UC Berkeley first. It supports series of model frameworks, PyTorch, scikit-learn, I don't know, XGBoost, TensorFlows, and stuff like that. It has RESTful API. It basically has some sort of cluster and resource management, and it's really good for kind of like latency if you want to optimize. So that's one of those libraries that you can just need to install it. It has a necessary infrastructure and supports for you to serve your model. Without, if you don't want to write your own, basically front end, back end, and stuff like that. The other one is like a TensorFlow serving. So if you are basically, especially if you do TensorFlow, but it has support for other models. It's also open source from Google. It serves a series of models. It's has a REST and gRPC, so like basically API calls, and it basically allows you to do some sort of like version management. Yeah, so overall, there's like if you use this managed services, there are some advantages. Basically, it's kind of like a real-time endpoint and low latencies. The deployments are easier, especially if you do something on GCP. They're kind of like they have auto scaling for the traffic, and they allow you to change between GPU and TPUs. But again, if you want to basically use everything from some sort of like out-of-the-box tools. Now, we're not going to go over, I'm just going to skim through this part because the code is there. But if you want to use TensorFlow serving, for your project, there are two types of servers, two types of binaries. Remember, we said that for model serving, you need that loader, you need that binary basically. So TensorFlow server has two types, TensorFlow model server universal. The TensorFlow model server, it's kind of like a more recent version. If you're targeting series like a more legacy hardwares, it might not work. So that's why they are basically saying that, well, this will work on most of the machines. So if you target legacy hardwares and you don't know if your customer, they have an old machine or new machines, then maybe use the one on the left. On the right, sorry, TensorFlow model server universal.
What exactly are these binaries?
It's all like a binary for loading your model and providing an API to make a call and get the result back from your model. And we're going to have a quick demo on it. Not demo, I'm just we'll skim through the thing. But so this will be example. So you basically install this TensorFlow model server. And this is a data set. Let's say we pass this. So you have this model, you train the model, you save the model, and then you want to basically load the model. So here up to this point, we just saved the model, and now you want to load the model. So you can basically load a TensorFlow using TensorFlow server. What's the port, API port that you want to basically load it, and where's the model? So this basically provides an IP and port which the model is served on. And now if you want to make a call, basically all you need to do is just using a request, send the request to the address with some headers information. And the header could be, what's the content time? It's just application JSON, simple as that. You send a request to the address that the model is being served. And this model, imagine, can be served on your local machine, could be on a VM that you have in the cloud, right? Or whatever, like let's say Cloud Run that you have, or like a Kubernetes. Within that, you install the TensorFlow server, you serve the model. When it comes up, it gives you an IPN port, and you provide that IPN port within your backend and frontend. So it's kind of like your front end gets an data from users, send it to the backend basically connects to that address, makes this request, gets it back, give it to the front end, and front end gives it to the user. Okay, so that becomes the idea. If you want to do so the reason these types of libraries are easier because they do everything for you. Like you don't need to have an API address, like you don't need to have a Flask and this and that. Just work with TensorFlow or work with Clipper. As soon as you load your model, it already also, when you serve it, it gives you the IPN port. You just need to make a call to that IPN port and say that this is the data, give me the result, and serve the result to the user. Does that make sense? All right, so we can pass from this. Again, the lab is there for you, so you can basically try it out. So Okay, so. So now we're going to talk about some patterns and infrastructures for the for model serving. So we have talked about this before. So we have either on-prem or basically on the cloud. Overall, when we talk about on-prem, the goal is that I want to train and deploy this model, send it to on-prem machine. You basically you need to always account for manually changing between hardwares because your model is deployed. So you're kind of responsible for having the code to change between GPU and CPU based on the time or based on the request. Let me give you one example over there. And what we were doing previously was that we had the model, and our model basically wasn't using GPU, but was if there was a GPU, it would have used it. If there was no GPU, it would use CPU. But what we were doing is that we were not at every point making a classification, for example, or regression. What we do, we had an agent. The agent basically is responsible for monitoring. It monitors the activity on the machine. If user is currently active and is doing work, because this is a hospital environment and doctors are working, you don't want your model in the background to run because it can make the model slow and it's kind of, you don't want to do that. So if you see there's activity and if there's basically activity by the user, not other activity, like active user basically there's activity or something, you pass this classification and you just wait. And when the activity goes down, basically your model comes back up and basically start going. So we were responsible for that passing down of the model, deciding if the model need to use CPU, GPU, or when the model need to do that. You are all responsible for all of this. Okay, it's kind of like it's your decision. Now, when it goes to the on cloud on the other end, well, you deploy to some sort of like a cloud services. And you don't need to basically worry about that part that, should I serve it now or not? Just you're already paying for infrastructure. The model is served. When the request comes, you don't need to worry about, I have too many requests. Those services, those cloud infrastructure, they will scale that up and down for you to be able to answer. So you see that there are more challenges if you do on-prem because you are more responsible. Like there's no other one there. It's like your team is responsible for having the code that works on scaling up and scaling down maybe. But in cloud, it's just all like a kind of like a done for you. So when it works on on-prem, you can use series of open sources libraries for on-prem like a TF serving, KF serving, NVIDIA, and we're going to go over those ones today. There are different binaries that you can use for serve the model on-prem. And also when we use on cloud, you all have seen that like you can use VM, Kubernetes, and cloud runs, cloud functions. They're all like basically available for you to use and like different microservices available for you to serve your model. Now, let's pass from this. So when it comes to the model servers overall, this basically that's the three things that we said you need. You need a model file, you need a data, and you need some sort of server, some sort of like a binaries that can load the model and make the connection between the model and provide some sort of like an API. And the request comes that goes to that API is either REST API or like a gRPC, and basically it sends it to the model, gets the result, and basically provides the result back. It's kind of like this three-piece becomes the main three-piece. So I'm just going to pass this. Now, when it comes to model servers, especially for on-prem, so you can work with TensorFlow serving. You can with something called Torch serve for PyTorch. There's an NVIDIA Triton, and there's a KF serving, and this is like from Kubeflow. So it's like this there are much more than this. Like this says MLFlow also has, another one. So like there are different libraries out there, but this four are kind of like an oldest one, and they have it in market more than the other ones. We start with the TensorFlow one. So for TensorFlow serving, it allows you with serve TensorFlow models, non-TensorFlow models, embedding models, vocabularies, features. It has batch and real time for inference. It does multi-model serving, and it gives you both gRPC and REST endpoints. Okay, so that's overall out-of-the-box integration if you just install or have the binary for TensorFlow serving. Now, if you go to, let me just quickly go over it. This is what happens basically under the hood of TensorFlow serving. So there is a client. There are basically three specific color coding. The blue is for the client, like when the request comes. Anything green comes from the serving perspective. Anything yellow is kind of like a pluggable implementation. So here you have TF servable, and TF servable could be your TensorFlow models basically. And here you have some file systems. So the TensorFlow servers basically has a loader, has some sort of source, and it has dynamic manager and servable handler. So source basically is responsible for system files and stuff like that. Okay, provide these binaries and stuff like that that you need for running this. Loader is responsible for loading models basically. You know, if you have model files, then basically loader's job is to load that. Then you have this dynamic manager. So dynamic manager is kind of responsible for, let's say you have series of models, and dynamic manager is responsible to know which one should be loaded and which one should be served. Kind of its job. So it has some version policy. Version policy, one example of version policy could be, you could even have different users being served different models based on the level. Is probably like a large models or like that. Like if you pay different grade, you get different types of models. So kind of like you could have a version policy. And servable handle is just, it's kind of like providing, think about it, providing that API to the client and making the connection to where the model is, like the dynamic manager. So that's what happens under the hood in TensorFlow server. I'm just going to pass through it because it's was just changing. The next one is the NVIDIA Triton. Well, it's built by NVIDIA for NVIDIA GPUs. It's kind of like first, it's also open source, of course. NVIDIA, you need to have the NVIDIA, so if the code is open source, it's fine. It allows you to work with TensorFlow, TensorIT, PyTorch, Onyx Runtime, and some of the other custom frameworks. It basically can access also any of these storages. So the model doesn't need to be on local. It has REST and gRPC. Overall, it's kind of look like this. So what you see here is that you have CPU and you have series of GPUs. Let's say you have this available. So basically, what the Triton does, on top you have client application, like let's say you have front end, and you have some libraries for Python, C++, whatever you basically have used. You could respond with HTTP. You could respond as like a gRPC. Now, inside the basically inside the Triton, it has a series of components. So it has a scheduler, which is responsible for scheduling and making the calls. It has supports for Onyx, TensorFlow, PyTorch, and whatever. These are the binaries that require. So that means if you're loading a model which is TensorFlow, it already has the TensorFlow binary for loader. With PyTorch, it has the PyTorch loader. So you don't need to provide that to Triton. So it has some C API for making an inference request and to get back the inference request. And it has model management, and model management, again, it's the same thing they just said, that if it's a TensorFlow, it knows exactly where to get the basically binary to load it and so on. And there is a model registry that it will have access to wherever you're storing your models. Basically, it can read from there. And it also will provide the HTTP. On bottom, basically what it has access to GPUs. CPUs, depending on what's required, it basically does back and forth between these items, these components. So that's the basically the Triton for the NVIDIA. It's if you do a quick search these days for, especially that because we're getting closer and closer, like the models become larger and larger. Lots of companies are kind of like going toward larger models. If you look at the job description these days, lots of time you actually see Triton as a requirement to know, like it's kind of like array, Triton, TensorRX, TensorRT, and Onyx. So these ones are becoming more popular and kind of like a must know if you're going to work with larger models or environments that where you actually hosting or training your own large language models. Because these are more like optimized in compared to certain frameworks. They are not going to be, if you're developing your own model and serving your own model. So, again, the overall here, basically, idea is that Kubeflow is, as we said, it's like is another one, but all of these are designed to be able to scale properly when there is a request and basically to scale up, scale down. So you have some front end, you have some back end. Similar to what we saw in the labs, you have a load balancer, which is just responsible to making this basically distribution of the traffic. And then here you have Tritons that comes after. You could basically have different Triton basically serving. If it's a GPU serving, if it's a CPU serving, and so on. So it basically similar to everything else that you have done. Like if you could basically have a VM, you could have a Kubernetes, and you can have your Triton sits over there and you use it for your serving. Now, the last one I think we have is just a Python from PyTorch. It's called TorchServe. And so TorchServe basically is from AWS and Facebook. It's batch and real-time multi-model. It supports REST endpoint. It has monitoring. And one of the interesting, I don't know if TensorFlow or others, they have that. TorchServe has A/B testing, which is pretty neat if you have a series of models and you want to see which one is better. So TorchServe has A/B testing. And it basically can handle different types of data. Now, so TorchServe, I think we did all of those. Yeah, and this is just under the hood of TorchServe and how does this will work. Similar to all of this, they have same components. They have some sort of like a model manager, like a version basically control. They will have something for accessing some sort of like a REST or gRPC. They will basically have access to model store. They can answer like some sort of like an API request, and internal pieces basically how to optimize for answering. Like if it's just a batch response, if it's like a real-time response. The kind of all of them, they have similar flavors. It's just some of the components might be different within. So, and the last one becomes KF serving. Again, this one is from Kubeflow. And this is what we did in the previous class. So imagine now you have the Kubernetes, and then you want to serve a model, actual ML model on the Kubernetes. So you can use KF serving, which is more like some sort of like a package support on Kubernetes for serving ML models. And basically it supports almost all of those models that you are seeing. There's kind of like you can load any libraries and basically any model to serve it. All right. So those are like the types of servers that you could use. The next thing now is going to be on scaling on your infrastructures. So I have a way I'm serving the model. Now we want to talk about it. Okay, how could you scale it? How could you basically respond to lots of requests? If you have all of a sudden lots of requests, what you need to do? So let's say you have this model and this data comes through, and all of a sudden you get this. All of this basically requests come through. If you don't have a proper way for handling a large amount of requests or high traffic, what happens here is that either your server goes down because it's just breaks, or your user basically starting basically getting errors or just waiting and they never get the response back. So you need to ahead of time account for how I can basically handle large amount of requests, like a high throughput and high basically requests. Now, why scaling is important? Because again, you receive lots of requests. The first types of scaling, this is kind of like a vertical scaling. So vertical scaling, I think we talked about in the previous class, but you can think about it again. It's like you have a machine. You have a rented this, and you're serving your model on this. When the request, basically the throughput goes up, like a amount of requests goes up, like you have lots of traffic. In the vertical scaling, what you do, you sell the machine, get a new machine. Or if it's rented, you basically give it back and you rent another machine. Right? So you kind of like, you change the machine type that you have rented. And the example that I used in the previous class was, you go on a road trip, you're 4 people in a car, and then now you have 4 other friends that they want to join you, and you're like, oh, we cannot sit in the same car. In the example of vertical scaling, you sell the car and you buy a van that 8 people can sit in. That becomes the idea of vertical scaling. On the other end, you have horizontal scaling, which the idea here is that, well, I'm not going to sell the car, right? We're just going to rent another car, another 4-person car, and then we go 2 cars. So in vertical and horizontal scaling, you basically rent, like you create, could be identical or could be different, but you basically, instead of changing your current machine, you just add additional machines. And we saw that in the VM lab or in Kubernetes lab, that we added this scaling. We defined we want a replica of the same machine. So when the request goes up, beyond certain maybe CPU footprint or beyond a certain number of requests, you basically scale up. That means you add another machine. And if the request goes down, you just simply remove the machine that you have added. So that basically means that, well, overall, we define, we prefer horizontal over vertical, because in horizontal, you scale up and scale down much easier. It's just kind of like when there's no traffic, you just go down. When there is traffic, you add. In vertical, you kind of responsible for the machine. You basically have bought a new machine. You have rented out a new machine, so it's your responsibility. But in the example that I told you is that you bought a new car, now you need to sell it. Well, it's kind of like if you have bought it. If you're renting it, then you are still responsible for the changes, or basically for all the process. So so that the between the horizontal and basically vertical scaling. Now, overall, when we talk about system architects, you need to basically keep something in mind. So you have hardware, operating system binary, and your app is sitting on it. We talk about VMs, and then especially when you do it with compute engines. So your VMs basically, you're renting a virtual machine. This virtual machine is it could be actual virtual, or it could be a physical machine. But a VM basically has an operating system binary and basically loads apps. The problem with VM, like a virtual concept, is every time you add one new VM, the same size, like an operating system size and everything, basically increases. That means if you think about this blue box operating system, when you rent a VM or when you create a VM on your machine, you need operating system to run and operate what happens inside the VM. And that operating system, normally it's like a couple of gigabytes. So every time you create one additional VM, you add couple of gigabytes added to your overall usage. So that makes the VM not suitable for scenarios when you actually need to create series of VM or like multiples. So overall, so you need some sort of like a VM management. You need a hypervisor and a scaler. You need some limitation, which that's just simply the binary and operating systems. But on the other end, it's containerization, and is when this is like the idea of like, okay, could we do something similar, but without that cost of keep adding and accounting for the operating system? So that's where the containerization comes to play. And here the idea is that machine has all the hardware and the operating system. So these two exist on your machine. All you need is the container runtime, which is your Docker when you install the Docker on your machine, for example. So this needs to exist on your machine in order to run a Docker. But then after that, every time you build that, you build a container, the only thing you need is the binary and libraries for running the code, whatever you need for that code. and the app itself. That's the only thing within a container, right? So you don't need to similar to the VM. So VM here, you see every time for any app, you need to have this blue, the operating system, which is a couple of gigabytes. Here in the containerization or containers, you don't need that. You basically, that is sitting here. And container runtime is responsible for translating basically whatever this one needs to run to your operating system. So,
But when we build a Docker, we write the Docker code, we generally specify something on the top, like Docker Ubuntu or Python or, but so isn't that kind of like an operating system that we're using, or what exactly is that?
sorry, you're saying that when you write the Docker file, you're saying that from Ubuntu.
Yeah, on the first line that we specify what kind of
Yeah, so when you have a Docker image and you convert it to you build on it, yes, you need some sort of like an operating system, but you normally have a slim version or something like that. In compared to the virtual machine, you're actually building a copy of the image, right? So it's still much cheaper overall. The other thing is that, well, if you think about a VM, you need to, you can build a VM. Everyone can build a VM, but everyone will be responsible for installing of everything in the VM. When you build a VM, just is a VM, so you need to install all the libraries and all the dependencies in order to run the pattern. And lots of time, it might not run. You might be able for some reason on your machine. For example, if you're a Linux user versus Mac, in the class we always have these issues. Certain students, they can install like I think Airflow is one of those, right? On the Linux, but on the Mac you cannot install, even if you do VM, right? It's kind of like you always have these issues with dependencies. But when you work with something like a containerized app, you don't, in the concept of Docker, you don't need to deal with any of those, right? So you just, when you build the app, as all those dependencies also as part of the build basically will be there. So you don't need to worry about those. But yeah, you still have some operating system that basically used. So, and again, the advantage, it requires less OS. It's kind of like an abstraction and easy deployment and runtime because you don't need to worry about certain things. Now, when it comes to basically container runtime, there are some open source technology that you can use. Some of them like are pretty popular. One of them is with the Docker itself as a runtime. It's pretty popular. It works with Linux, it works on Windows. Now, if you think about within the container orchestration, what happens? So you have some, when you run on your Docker on your machine, if you look, you have some sort of like, if you go Docker PS, you see like some web schedule, like in details, you have a scheduler, you have some sort of like a manager. So this, technically what happens, you have service management, you have some scheduling, and you have some resource management. And they are doing different things. So resource management is just responsible for the resource, what's available on the machine, how much I can use. Scheduling is kind of responsible for scheduling a task, what tasks need to be done based on what's available, doing the queuing for you. And the service management is just responsible for the service part, like you have series of runtime, like an application that you're running, and basically that service management, it just manages that part of the work. There's more like a starting abstract, and as it goes on, it becomes more like toward the hardwares. Now, there are a couple of popular tools. Docker Swarm is one of those, and the Kubernetes is another one. So these two are pretty popular as some sort of like orchestration tools for containerized app. If you remember in the Kubernetes lab, when we defined what's Kubernetes, we said that it's basically a platform for containerized applications. Okay, so if you deal with these two, this containerized app, these two are pretty popular that you can work with. All right, so page here. Second. Okay, now, so let's talk about the online inference. We still have some time before we take a break. So when it comes to online inference, so you have some observation, you have some sort of like an API. Most of the time it's kind of like a REST API. You send a request, and then this basically, let's assume this is your backend, and just basically makes the communication to the model, gets the response back, and then provides that response to the user. That's the prediction, right? So in online inference, which is not like a batch inference, so the result it should be right away. So you basically get one single request, and you process it, get the result, send it back to the user. So when you deal with online basically request, you need to think about a couple of pieces. So observation is the part that you get the data. There's this part that goes between a REST API and the model, and there's this part which is does the prediction, right? And then we're going to see that how this can impact the overall basically gating metrics of your model. So we talked about you have latency, you have throughput, and you have costs. So whenever you hear the term latency, becomes observation through prediction in online models. From the moment data comes through to the moment data receives to the user. That becomes the definition of latency. When you talk about throughput, you're referring to the communication with your backend and your model. How much data could go from your backend to the model and come back as a response? That defines your throughput. And when you talk about cost, it becomes all of this. How much cost do I have for serving this model? And like this could be the cost of like a cloud infrastructure, or it could be other costs related to the model if this model is deployed at the edge. Now, when we want to do inference optimization for online models, the first thing we need to think about is that, well, the easiest thing to optimize for is the infrastructure, right? So you can basically optimize the infrastructure with what you use, like the types of GPUs, TPUs that you use for optimizing the inference speed or like throughput. You can optimize for your model architect, especially when we deal with online models. If you are doing online models and neural network, quantization, pruning, those are kind of like a must do. It's kind of like, because if you don't quantize your model, if you don't prune your model, you might have a large model that lots of the weights and parameters that this model has, they don't do anything, and they just make your model slower and more costly for the inference. So you need to do certain model architectural, basically, optimizations. And the last one is just like a compilation, and that comes around like, well, how you actually compile the model? How do you load this model, right? An example of this could be are you serving this model in Python versus you're serving it in C++? Right? Those two could have a different cost. Are you, I don't know, using Triton, or are you using just simple TensorFlow, basically binary loader? Okay. Those are basically have different costs and different speeds. So there are some additional optimization that you can do for online inference. One of them is the data source, data store, and basically data store. You can think about adding some sort of like a feature store for optimization or reading data fast or pre-compute data. That could be one. So this becomes an example of these popular ones that we have, which we talked about it before. But this Amazon DynaDB, memory store, big table, cloud data. So these are kind of like a scalable databases that you can use for like a quick read, especially for online inference, where the millisecond is really important. So you can pre-compute data and basically have those data ready for the inference. There's differences between this. Some of those basically can can have slowly some changes in the data. Some of those are kind of like a fixed. So you need to basically read about those to see which one is better for your work or for your product. But again, just be sure that as it says, indicates here, and this is the second time we say that today, they're pretty expensive. So just use them carefully if you actually need those. So now when it comes to data, so all of this up to this point, we talk about batch inference, we talk about online inference, and all of this is kind of like a way around serving the model. Now we want to talk about, well, how about the data part, like the data processing of for these models. So if you think about here, observation to REST API, that's the part that you do certain data pre-processing. Like you do something on your data, make it ready in order to pass it to the model to make a prediction. And then that data goes to your model and comes back. Now, when we talk about data pre-processing, these are types of things that could happen from your data cleaning. When you serve a model, data comes dirty. Right? This reality of the data that comes from customer side is like the data is not good. So, and you don't have much time to clean the data. So you need to basically optimize the ETL pipeline. So if you think about it, we saw ETL pipeline before. During the training, ETL pipeline is really different in compared to serving. During the training, we had different goals. We wanted to be able to have our accelerators and our CPUs basically to basically be busy as much as possible because we are renting it, right? We pay for it. Here, your goal is kind of different because you want to be sure that you can do all of these pre-processing as quick as possible. It's because user is waiting for the result. Right, so it's not about the GPU, your GPU, it's about that the user is waiting for the response. So you could be doing the cleaning, feature tuning, like construction, like a feature crosses and stuff like that. You could do some sort of like a transformation and you could do some sort of feature selection. All of this, you either need to find a way to do them in parallel or basically optimize for doing it, or, just keep this in mind. If the slower this process, the slower the inference response that you have. So it's not just about your model. You could have a model that's pretty fast, but your data pre-processing pipeline could be slow, and that becomes the bottleneck of the process. All right, I'm going to just pass this. So the next thing is that post-processing. So if I serve the model and my model is fast, good. Pre-processing pipeline is also fast. But as soon as the model provides results, well, I need to do a series of things on this result, the model, before I give it to the user, and that part could be slow. Right, so that's another challenge that you have, is that you need to be sure that the post-processing of the result is also fast. Especially think about most of you in your project, you are doing some sort of like a LLM chatbot and stuff like that. And how many of you have looked actually at the response part after you have a result through the time that you provide it to the user? It comes on the UI. How fast is that part? Have you looked into it?
Depends on what do I say, what thing is serving. So I tried once through my local, like my own PCS hosting the LLM. It was very slow in the number of tokens.
After you already have the response from the model, just showing it basically.
No, the response generation from the model was slow.
No, but let's say your model provides a response, and you basically need to do something with that response and give it to the user. That part of the pipeline. Have you looked to see that if you can optimize that part? He's laughing. He's like, no, we haven't. So that becomes another thing, right? Because it could be like you already have the response, but it takes, I don't know, even a second, 2 seconds for you to massage this response, make it in a proper format. But especially when it comes to the concept of like a chatbot, you do a series of guardrails, right? If you think about those guardrails, there's no post-processing of the result. Those could easily make the response much slower. And if you don't have that part to be optimized, because you could have a response and then let's say the response goes through a guardrail and guardrails basically reject that. You cannot pass it to the user, you need to redo. Now, if this process now becomes a couple of seconds, the user basically sent a request like 10 seconds ago, they are still like a loading in the background, try to give the response, then that becomes problematic. Right, so if your project has some sort of like a guardrails that your response goes through, take a look to see how you can optimize that. Like maybe you can parallelize those, like you don't need to sequentially pass it to the guardrails. You can basically do at the same time, you know? So just look for those ones. Okay, so the next one is the batch inference. So we're going to just talk about some patterns and infrastructure. Now here, the difference here is that you receive this request. And again, as I said before, you don't respond to the users. You collect those, you have some scheduling. Either you, depending on the also application. So you could have an application that users send a request and they don't expect the answer now. You like, we will, whenever it's ready. Have you ever filled any form or something and you get an email back? We will update you whenever it's done. Right, those are like a batch response. So what they do is that they have some policies. The policy could be either, well, you only process it if you have certain numbers, right? So that could be the policy. Some other companies, they don't even do that. Why? Because you are renting GPUs and you're like, okay, I don't want for every batch to go start the GPU and make a process. So I collect all of this, maybe through the end of the night. End of the night, for the certain period of time, 1 hour, 2 hours, I rent a GPU and process everything. Then I basically return the GPU and I post-process the result and give it back to the user. So depending on how is your infrastructure, which one makes better sense for your company, you can decide when do you want it to schedule it right away when the batch is ready, or you schedule it on some sort of like a time interval on every night or every, I don't know, certain hours. And then you will basically have the results and you add the result to a database. And if you need to update a user, you send the update to a user, your basically process is done. So basically come check out your application. And some of the example of that could be, if you think about like a banking, certain banking application, when you fill it, you never get a quick response. It's like we will process it within 2-3 days and just let you know. Or it's kind of like, that's like a batch processing. Now, one of the advantages that batching has, it's, well, you don't need caching. All right, so for batch processing, you don't need caching. That means you don't need quick in-memory data. You don't need pre-computed, basically, like a data it sits in some sort of like a memory store, which are expensive. If you do batching, you technically don't need that. So that itself is basically reduced in the cost, overall cost that you have. There are some limitations with batching. Well, the first thing is that the updates are basically longer, but prediction are based on the older data. So that means you could have an application that when your request comes in, the day after you give the response back, but maybe the day after that data is already has changed and is like this is not like acceptable data anymore. So that could be a challenge for that. So another example is that, for example, for recommendations, if you have a recommendation that user comes and they basically want they have some request and you're like, oh, we give you some recommendation back. That recommendation could work depending on the application. For certain applications, if you're dealing with, I don't know, like I have a recommendation for a hotel that I want to basically book. And I put a request and this agency says that we will basically give you some recommendation. And tonight they send me an update. But maybe I have changed my mind tonight about like now I'm looking at a different place that I want to go. Right, so it's kind of like depending on the application, this request might be valid or not. When you deal with batch, you don't optimize for time, you optimize for throughput. So that's where having a larger, better GPUs, which makes more sense. If you do online, maybe you don't need a larger GPU, you need more GPUs, smaller GPUs to basically, you can answer a series of basically call. When you do batch, because you want to make a call and pass 2,000 basically data point at a time, then you need a larger GPU. So that's where the throughput becomes more important. All right, so, and yeah, again, accelerator like GPUs and TPUs, they become more important. Now let's think about a couple of use cases. So if you go some of the basically this e-commerce websites, so you have series of a scheduler. So this schedule basically runs maybe every week, and then every week basically it goes to the market, it collects some data, and based on that it creates some sort of like a recommendation. You have some caching. If you work with the e-commerce, basically one of the easiest thing is that to have some caching, because doesn't matter who's the user, you always use the same products. So it's kind of like if you have cached this once, maybe you store it so you can use it again. It basically helps you, like this concept of caching helps you to make better prediction. But overall, in e-commerce, it's like a batch inference. You can think about it actually for online inference. User could come to your website and they want to buy it right now. But if you think about it, maybe the company actually doesn't do a similarity or recommendation right now for you, because that could be pre-computed result for, because if you think about it, if I'm buying a sports shoes Nike, there are some similarities, kind of like a collaborative filtering. There's some similarity about this product that I already know which other product are similar. So I already have those as like a batch computed, and I just give it to you. So it's not technically with respect to your need. So that could be one example. Now, when it comes to sentiment analysis on the other end, well, you technically don't need anything real time. User comes right through review and you basically process that review. You can have a larger models and stuff like that. You basically make a respond, and technically don't do respond to user. You basically have some database that you're updating. So sentiment analysis, most of the time, just batch data. Doesn't need to be real time. On the other end, when we're basically dealing with demand forecasting, well, anyone here does demand forecasting for the project? Okay, what do you do?
Stock market prediction.
Stock market prediction.
You're changing the scope. But basically you have a store and every day it gets some items. We log those on a daily basis and you're supposed
So
to.
you do batch processing over there,
Yes.
right? Batch inference. Okay, so similar idea basically. It's kind of like you don't need to things be real time. You just do some batch. Of course, not for stock market. That's good that you guys have changed the idea. Because the stock market, you want it to be much faster, much quicker. All right, so let's take a break and then we continue from here. Okay, let's continue.
It doesn't matter. मेरे पास इसका domain है.
इससे फर्क नहीं पड़ता. इसे बहुत ऑटो स्केलिंग
All right, so the next thing we're going to go over is just how to ensure that basically use series of like a distributed basically pipeline or batching for your data to pass through models. So if you have a batch data, you can basically do a series of reprocessing on this batch. It could be done in parallel or something, again, with a similar what we were talking about. If you deal with streaming on the other end, streaming data or the type of data that could be coming from sensors, and you still need to be able to, like some sort of like a performant way, process that data, make it ready for your model. And we previously, again, we have talked about ETL, but we talk about ETL for data training, like during the training of your model. Now here, the focus on the ETL will be that, well, it's for serving. So you want to be sure that this data pipeline is basically performant enough that can pass the data quickly to the model. Now, so what you need to do, think about the ETL part. You have extract, you have a transform, and you have load. And those parts basically, if you think about, so the extract, you have different data sources. Let's say I have an app, And my app, what it does, it basically, user asks a question and my app, let's say, for example, I'm just doing like an Uber, basically providing service. So user asks a question and on the other end, basically, I have a call to an API, see what's the weather. I call into another API and say that what's the traffic looks like. I make a call to somewhere else and say that how many drivers do we have available? So data comes from all different sources. Like you need to be able to quickly basically have this data. Most of the time, these data are pre-computed for certain things. You need to basically load this. So if the data is ready, let's say pre-computed or somewhere, you need to extract them. So you need to be able to extract means to quickly read them from different places, gather them into one place. You need to do transform, extract, transform, and basically do all the necessary pre-processing that you need. You need to load it on your basically on your let's say cache or wherever it is that you want to serve it to your model, and you pass it to your model, and then you get an answer, and you basically provide that answer. So this is the general ETL pipeline that you can basically use. Now, how could I optimize this? One example will be that, well, let's assume that the extract part is optimized. Like you quickly, as quick as possible, you are reading the data. Now the transform part you want to work on. And the transform part, instead of sequentially process your data, you basically do some sort of like a multi-processing, like some sort of like you have different workers. Each worker does a different job. So it's not sequential, your pipeline. So you have different workers. All of them basically work together to pre-process the data, make the data ready, and then you load the data to make the final prediction. So that becomes a scenario where you have a bottleneck on your transform, like on the pre-processing that you do. Now, one way of, or like a couple of ways, like libraries that you can use to make that transform, that part, basically extract, transform, load more optimized, is to use things like Apache Beam, cloud data flows and stuff like that. So these are kind of like Spark and Beam, cloud data flow. They are, especially when you work with like a large volume of data and you want a way of quickly be able to process, match, load the data into the model. So these libraries are become pretty useful. They can basically access different types of data. Especially these days, I think, I don't know if you have heard of, like a Parquet is one of those data types that are more optimized in compared to like a CSV and stuff like that. So, but the benefit of this basically tools are, they can basically help you with streamline the data from the source onto the model and get the response back. And so again, now the one quick thing that I think we previously talked about it, but you just put all of this in one picture. Let's say you are working on an app, and as part of your app, you basically need to read data from different sources. Why these markers are here? I'm thinking. So let's say, so you have this, you have data comes from different sources. And let's say these sources are not part of your environment. Like you have access to this, but it's not part of your environment. So, let's say user have a request, and let's assume for now we're doing a batch inference. Okay, so it's not online. So user have a request, and what you need to do based on the user request to go collect data from wherever data is necessary, because not every user will have similar requests. So let's say there are different places that you can get the data from, and it depends on the user request. The user requests come through. You have this query. None of this works, and user data comes through, and based on the user data, you decided that okay, I'm going to get some of this comes. So Now, what we basically here say that, like, imagine you have this pops up, okay? And this pops up in your, sorry, not like that. As we get closer to the end of the semester, these markers, they're gone, just sitting over there. This one. So, if user query comes, you can basically go get this data. Now, instead of doing that, so let's say I have this pops up, which we talked about it in the lab before. So you have this publisher and you have this subscriber. And you basically have created this topics already, okay? So I don't need to wait for user to send me a request. I already have these topics that I'm listening to. And every 1 hour or something, basically these topics will be updated. This topic basically is getting notified, hey, there is a new batch of data ready if you want it. So this topic basically updates the subscriber, basically sending a message to, let's call this T, subscriber basically. And so the subscriber is like, okay, well, there is a new message that we basically we are aware of. We want to get that message. Then you have something, I don't know, like we're just talking with your friends over there. Like, let's say you have this, like a cloud runs. And this cloud runs basically responsible for getting the data. So every subscriber, when there's a data, they basically, there's this service goes on, and so on, right? So all of this part is kind of like this streaming this data. So it's like it's technically not online streaming because it's like a kind of like a batch. But still, if you have a streaming data, you still can use pops up. It's just a stream data comes through. So this will basically run, and this gets the data. Now here within the cloud run, you do transforms. Transforms, and so on. You do some pre-processing on the data when you receive it, you transform it, and you put it somewhere else, like a storage, ST2, and so on. It's like a storage. And then you have this basically data ready, and user comes now, user have a request for doing something. You don't need to do this. You basically need to load the data from the storage, wherever it's there, and then process and pass it to the user. Give it the answer to the user. Now, if you want to all of this to be some sort of like a streaming and become more optimized, so the idea will be that this part, the transform, load, and all of this, you can use one of these services, right? So instead of we having maybe this cloud run that does this individual transform work for us, you have some streaming service that when the pops up says that, well, there are messages, there are data already, you have something like Cloud Data Flow, Kafka, Spark, Hadoop, that they are basically responsible for getting those messages, process those messages, and put them somewhere else. Okay, so this part will be replaced with one of those services for the load, transform, extract, load, transform. Without this, it kind of becomes individual microservices, basically. Okay, so it's kind of like, depending on what you are trying to do, but at the end, all of this basically, they do the same thing. Of course, this one is more optimized for a large amount of data. Why? Because if you do something like this, this is working fine if you have a small amount of data coming through. If you have now, if you're working in a company that is like a millions amount of data comes through, like this APIs, this microservice is not going to work. It's going to be so costly, you're basically going to go out of budget so quick. Because this is normally good for quick services that you don't want it and put it back. Now, if you have a lot of service data that comes through, you need a streaming processing. You don't need microservices. You need something that's just running and process the data on a large scale and basically save it. So depending on what you are doing, how much data, how much volume of data that you have, traffic you have, you can decide that do I need microservice or do I need basically some streaming processing? Okay. So, all right, so let's go here. All right, so that was about model serving, which all of you at this point within the next 2 weeks, something you need to serve your model. And I think that your next deadline technically is model monitoring. You need to have a way to monitor your model. So first thing is that we're going to talk about why model monitoring matters. So we all have seen up to this point, all this life cycle that you have been going through for your project. We have been talking about in the class from building the model, evaluating, productionizing, now testing, deployment, and now it comes around monitoring. Okay, now we have this model, it's deployed. What about it? Like, will it work? Is there any problem with it? How can we be notified and how can we basically fix it? That's just a really important one. You know, an ounce of prevention is worth a pound of cure, right? So it's like, it's always keep in mind, it's like it's better for you to know if something is going to break down versus if something breaks down. And if you think about, for example, in manufacturing, so one of the actually really common practices for using machine learning, predictive modeling is in manufacturing, especially in production line. So what we do, we try to predict ahead of time if the machine is going to break and when it's going to break. If I know this pipeline, this machine is going to break, what would you do? It's like you schedule basically some mechanic that comes like, hey, over this time period, we're going to shut down this and fix it. Whereas if it breaks down, then you need to change so many pieces and now it's going to take much longer. So if in manufacturing, one of the things we do is like a CNC machines. So I don't know if you ever have done manufacturing classes or not in university before, but we had it in industrial engineering. So it's kind of like a CNC machines, when they work, they produce like a vibration, right? So what you do, you monitor this vibration, measure this vibration. So basically you have some machines like sitting near the CNC machine and you monitor this vibration. The vibration on CNC machines are pretty standard. So it's like they are within certain interval. When a CNC machine is getting to the time that is going to fail, you start seeing fluctuation in the vibration. That becomes a good indicator of, well, this machine needs some services. Depending on how much this vibration goes, you can also predict the time remaining to a breakdown. So that's one of the ways that in manufacturing, we try to predict like if the machine is going to break down or not. So when we talk about why we need monitoring, well, the first thing is that data skew. And data skew is like, well, remember anytime you heard the term skew as when two batches of the data are different. That becomes skew. Drift becomes anything that's time-based, like a time series. So if you hear the term skew, train serving skew means that I built the model over the data for the last 8 months, and it took 4 months to build this model. Now, as soon as I serve it, it doesn't work. Because within that 4 months, there has been a skew in the data that you used. So that becomes the concept of a skew. The other one is like a model staleness, and it's like a model staleness is like when the idea of like there has been changes in environment, there has been changes in basically consumer or like a label changes. There's like a models still, the model, they don't work anymore. And negative feedback loop is kind of like that's the part that you want to be sure you have some sort of like a feedback loop from the user as part of the monitoring. Now, when you monitor in your pipeline, in your basically product, you have 2 types of monitoring. ML monitoring, anything that's functional around your model and your data pipeline. And then you have system monitoring. So these are two different. Most of the time, the system monitoring comes out of the box based on where you are serving it. So when you are using all of this tool like on GCP, like Cloud Functions or like VM, Kubernetes, the first time when you deploy any or when you start a VM, you see by default it has monitoring section. And when you go to that monitoring section, it gives you information about CPU, RAM, throughputs, traffics, and all of this. So most of these platforms, they have this out of the box for you. But that one is the thing that you don't have, right? So and when it comes to the ML monitoring, you are building a model. You know that better than anyone what you need to monitor for. Because if you think about it, if I'm building something and I have done all this study around it, validation, I might have a good idea like what should be monitored because I know that part might actually break. Versus out of the box, like a metrics, which they don't make sense, right? So you basically need to account for predictive performance, how good is the model, is this accuracy of the model remains the same, if the model always is like a confidence with the same, within the same interval. Is there any change in the data that comes through? Is there change in overall like metrics that we have used during training? That means if during the training a phone score across different slices was within this range, is this remaining constant or is like basically changing? And the last one, just characteristics of the future, like a statistics of your data. So monitoring becomes the last part of your overall pipeline. But what's important is that, as we have talked about this will trigger almost to the start. Like it could basically take you back to the scoping to redo this, redo the project because it's something that you thought is going to work. And now after monitoring, you're like, well, it doesn't work. Right, so this cycle basically doesn't end here. Now, when it comes to observability here, so overall, the observation in ML model is, so we have different observability, we say. One of them is around your model behavior, like overall, it's like its model easy to understand. But one is around there's like an internal part of this model. Can you see the flow of the data? Can you understand how the data goes through your model? Can you basically point out where is the problem? Can you detect those? So overall, observability comes from the system, control system theories, and basically they're closely linked with the controllability. So there are some architects that they make observability difficult. Cloud-based systems, they're making it challenging because you're dealing with so many components in the cloud, so it's hard for you to basically follow the flow of the data. Containerized infrastructures, of course, it makes it much more difficult because it's container. So if you think about the simple example, when you run a Docker, and if you actually want to know what happens to it, you actually need to log kind of into that one container from within the container, try to access the logs. And so it's not that straightforward for observability. Distributed systems or microservices, these are all becomes more challenging when you deal with, when you try to be sure that you can observe everything and basically, so you need to think ahead of time. If observability is really important for you for certain applications, there are certain types of basically services or infrastructures maybe you cannot use or maybe you should not basically be using. Now, deep observability basically means that, well, don't just stop at the top level metrics. Domain knowledge is always important. There are some tools like TFMA that basically gives you really good details. And, you know, it just is good with both supervised and unsupervised. So it doesn't need to just be supervised. But what's the overall goal of observability in your pipeline? When you have this monitoring pipeline, the overall goal is that it should be alertable, it should be actionable. Okay. What's alertable? Alertable means that if something goes down, it needs to let you know, or it needs to be ahead of time predict for you. Actionable, it should be able to tell you also what's wrong. How basically, so actually, I can give you one example here. So there's this, well, I have dealt this in industry before. We call it actually, ostrich award. So if, during the, in cybersecurity, if I just keep calling you and tell you that you have issues, and if you, even if you have issues, the problem that we end up with was, everyone will love it. They were like, wow, how did you detect it? But I'm not gonna buy it from you. So we call it an ostrich award. Why? Because if you keep calling me and say that I have issues and you don't give me a solution, I'm responsible to finding the solution myself. So if I don't buy it from you, I'm not legally, I'm not liable because I didn't know about the problem. Right? You hear that? So lots of times that we dealt with the CISO, CIOs like in hospital, and they're like, I tell you that I'm selling you the perfect product. It detects all your problems. I don't have a solution for you yet because we were just a startup. And we're like, oh, I don't want to buy it. We call that an ostrich award. So that basically means the same thing. Alertable, actionable. If you alert me, but you don't have any action for it, like there's no solution, what do you want me to do? So if you build, think about this. You are the ML engineer, you're building the pipeline, you're building the monitoring pipeline, but you might not be the person who's going to take action on it. So you know better than anyone what should be the action if something happened. So if you just create an alert and that alert goes to a different team, now they don't know what to do with this alert, that becomes a problem. So if you have an alert because you know this alert, it should, you monitored for it. So you also kind of know what action needs to be taken. So be sure that's kind of like an actionable alert. It's not just an alert that something is wrong. Does it make sense? So now when it comes to monitoring, let's talk about the targets, the output of your model. Okay. So it's actually input and output. So when you think about the data, data comes to your model. There's a data in, there's a model, there's a data out. Right? So when you think about the input to your model, all of you, your pipeline, which you will have for your demo, it should have a schema validation. It should have a distribution validation. For any request, you basically need to validate. Does this match the schema of the data that my model expects? Yes? Great. No? You need to have certain action for it. And we talk about this action. What could be the actions? Could be you either reject it, or depending on what's the change in the schema, you could either just accept it and just start counting, creating some sort of like a frequency count. If I keep seeing requests like this, then I will update my schema, or you could actually have a schema that updates itself as it goes. When it comes to the distribution, also similar. Like if you see data that all of a sudden is from different range of age distribution, even if you process it, you need to create an alert and some sort of like a cumulative alert, because it needs to show you over time if there has been changes over this distribution of this data. Because those are sometimes a really good sign of the drift, and if you don't detect data drift ahead of early enough, your model performance will go down by default. Then it's basically model version, and then the output. So definitely monitor for the output of your model. It's not just output. An output of a model could easily be a sign of the performance of model goes down. Again, if it's a classification and binary, if you just simply monitor, this is just one example. Simply monitor for the range of or the region which the model is not confident, like 30% to 70% range in a binary classification. During the training, you only had 5% of the data falling here. Now, during the serving, over time, now you have 10% of the data keep coming there, 15%. That means your model keep opening files or have a request, and the model basically says, I don't know, 50%, 60%, 45%, right? So if that range is that value is increasing, that itself could be a sign that, okay, the model is not, or model is decaying, or the data is different, the model doesn't know what to respond. Yeah, so okay, just check for the following thing, input values that fall within a range. this change of the distributions or basically per slice, that's also important. So it's slicing is not only a metric that you do during validation. It should be actually during your serving also, because if you remember, if you don't slice your data, what happens? If you only look at the aggregated result or average result, you only know the answer with respect to average. Because you might be doing perfect, 99% on average, but for certain slice, you're actually doing 0%. Like they don't take any benefits. So you need to do the slicing there. So that's an idea of like a difference between training data, live data, if there's a significant statistical differences between them. So that's a sign of that you need to basically have some sort of like a maybe retraining or validation. Now, when it comes to ML engineering, what we monitor for latency, memory, like input, output, memory, disk utilization, how often system is uptime, auditabilities. Like from ML engineering perspective, then you also have software engineering basic things that you monitor for. The HTTP request that basically receiving, you monitor for that. You can basically have entering or leaving a function, user logins, reading or writing from this. These are like different things that you can monitor for. Series of the software engineering ones by default, again, come from the tools that you are using. For some of the ML engineering ones, also like those are also these days GCP, Azure, AWS. They also have most of those out of the box. The only ones that is kind of like a bespoke, it's the one that you deal with like a data, types of data, input, output data, distributions, and stuff like that. Those are kind of like a bespoke. Now, logging, well, one of the ways to add observability to any pipeline is just log, right? Well, I remember at the beginning of the class, I told you to almost log everything at first, because well, at first, technically, you don't know what's more important. You don't know what you should log for. So it's an easy practice to log as much as possible. Over time, you get some sense of what's more important, which log it was necessary, which log is you don't need it, you can drop it. At first, you might not know. It's kind of like it's a better practice for your observability to add logs as much as possible and just basically reduce it slowly. And just the definition of the log is an immutable timestamp record of discrete events. Just that's a log, right? And you all are using log in your product, right? So when I don't know if you have worked on your dashboard, monitoring dashboard or not, but that log becomes a good thing for your adding to visualization to your dashboards. So out of the box, there are the following logging systems available. Google Cloud Monitoring, like when you're using a Google GCP for your if you use for your product, if you simply just go to logging, if you enable the API, basically everything is logged. It has cost, of course, but that's one way. An easy way, if you don't want to pay for a cost, something like that, is when your pipeline is running, write the log to a bucket. And then whenever you want to basically parse it out, you use some sort of like a log scale or some sort of parser, read from the bucket, parse out the logs, convert them to some format, and then pass it to a dashboard or something. Or you could have simply all your logs that goes to a bucket, and you could use something like a Power BI or Tableau on your local machine, connect it to your bucket, reads the data, and create a dashboard over there. That's also possible. So it doesn't need to be services. You could use any tool that you're more comfortable with for building a dashboard and logging. So advantages of that were easy to generate, great when it comes, like it could have lots of details. Disadvantage of logs are, well, it's if you log too much, it makes your pipeline slow. That's the reality of it. The aggregation of the logs becomes expensive. So if you have lots of logs and now you need to do something about it, it's kind of becomes really expensive and really slow. And then maintaining of the log also over time is not that easy. So lots of time you actually, at least my experience was that lots of time when you log, within a certain period, if you work with the log, you work. Otherwise, you never actually go back to those logs. It's like it's gone. But when you work with customer data, you cannot get rid of logs because it's of like a regulations. So certain regulation requires you to basically have these logs, and you need to store those logs basically. So you need to come up with a way to compress the logs because you don't need them in a raw format. So maybe you compress them and then store the compressed basically version of the log, especially when you have lots of them. So in machine learning, which areas we can log for? Basically log for anything around the model input output. Anytime you have something, all of a sudden there's a feature missing, maybe you create some sort of like a alert log. If you notice there's a big shift in the distribution, a schema, you create some sort of like a red flag log, like an alert or critical or something like that. So, and this is just a overall idea of like about the logs. You have seen all log is unstructured text. You need to some sort of like a pre-processing on the logs, and then you need some sort of like build some sort of like a dashboard for understanding the logs. Because without a dashboard, the logs are just logs. It's not easy to read. Now, what are the other benefits of logging? New training data. So think about this. You collect logs, and logs comes from customer environment. And again, this is depending on how much data you can collect, or you're allowed to collect, basically. But what you could do is that you could have series of basically pipeline with supervision, active learning, direct labeling, whatever you're using for labeling, to run over the logs, and portion of these logs that is useful, you basically run over it, you label it, store it in the place that's ready for your retraining pipeline. So think about this. You have a pipeline that's running. Data comes through, log comes through. Example of this could be, let's say for your chatbot, you're all doing the chatbot, most of you. I don't know if any one of you has in your chatbot has some sort of like a critic or some sort of like an intent classifier or something like that in your chatbot. Idea of critic is that when you like imagine you have a query and you make this query and you send a response back, you send basically the query, and that query you have some, let's say if you do a RAG, for example, you get some response back. Among this, which one you're going to use, right? So one scenario could be you just simply pick the top one. Another scenario could be you have some model that it's a ranking model, right? So I have a ranking model. This ranking model, I get series of response, and basically it ranks them for you in order, not based on this ranking model is not based on the similarity score that you do over the embedding. It's just it's a pre-trained model that also does the ranking for you. And based on this, you decided I'm going to pick, for example, this one, and you return this to the user as an answer. Now, user have an option. Basically, they either like it or not. Let's say user gives a thumbs down or repeated the question. Now, when you log this, so your log could be around what was this ones, what was this like top 5 that you received, which one you selected among them, and what was the user's ranking. They can get it as a positive, negative response. Over time, your goal is that to update this ranking model to know that to make it better and better. It's okay, you have a perfect feedback from user if user like the answer or not. So you can basically collect this data using logs. Over time, when you reach to a certain threshold, like you count how many times you get thumbs down. If it goes below certain accuracy, that will trigger a retraining for this or calibration for that. Now you have a bunch of new data that you labeled. Basically, is labeled by the user if they like the answer or not, right? And you use that to update somehow your ranking, and this pipeline could continue. So that could be an idea if you have a ranker. If you think about another example, let's say you have like something like an intent classifier. Intent classifier means that you're interacting with user and you kind of estimate what user wants to do. Based on that, you bring a different expert up. And then the user is like, well, I didn't ask you that. I want this. So you're like, you count that, okay, my intent classifier did a mistake. You count this as like these feedbacks, and when it goes to a certain threshold, basically you update the model, train the model. So without logging, this new data, it becomes impossible. You don't have it. So you need to have log, account for this new data, collect the negative feedback or positive feedback that user had. So later you can do some sort of like retraining. But these are like just simple example of labeling. So direct labeling is when you get the user feedback. Manual labeling is that you just have that feedback. Most of the users, maybe they don't provide you feedback, not directly, but there are some ways that you can, based on the interaction, to understand if I should retrain, or like what should be the label. Like if they repeat the question multiple times, that means they didn't like the answer or they don't understand the language. Then you could do active learning and with supervision. And active learning, we talked about this, is the idea like, if I have lots of data, maybe I shouldn't label everything, or maybe I only need to label part of the data, like a space that I think is more beneficial for my model accuracy. Not everything else is useful. Instead of label everything, you only label part that your model is doing bad on. And with supervision, the idea was that, well, you basically create series of a smaller classifier, use those like to every one of those basically label the data. You have some weighted mechanism among those. You build this generator, and you have this also like a discriminator, like a classifying the data. And that basically easiest library for that, it could be is like the Snarkle, right? So that becomes a weak supervision. Anyway, so that's the benefit of logging. Any question? All right, so now the next thing when it comes around the model monitoring is like a tracing. Now, there's some challenges when it comes especially to monolithic systems or basically distributed systems. And that's where you have series of basically modules running, and then this log comes through. So that becomes a little challenging when we deal with the distribution, because you need to ensure that the time and the trace is exactly, can take you back to where the problem was, especially again, when you have distribution. Now, when you, and the other thing is that like if you do distributed tracing in the cloud, that's also a similar story. So you have different services. They are basically doing different things. And this log basically is going to be written into the cloud. You still need to be sure that you basically have a correct way of logging. So there's no overlap over the two data points. And you also, if one break, like what happens if this one broke down, like internet was bad for the moment, and when the internet comes up, what happens to all that log that you accumulated, right? Basically, how do you send that? So, any opinion if what happens? Like, let's say you have a service, and all of a sudden, this one of them was offline, but it comes online, and you have like hours of logs. What would you do?
Keep a copy of it and eventually update the main log.
How eventually? Like when?
And there is like low, usage of that service. So like if we're monitoring it and there is low usage and we can use that throughput.
That's really a great point. So it's like if all of a sudden when the service comes up and I was like, okay, I'm starting sending like thousands of logs. What happens? The network traffic goes up, right? Especially if you work behind the firewalls in like an organization, IT shuts you down quickly because you're like, oh, you're using too much traffic. There is some sort of like a control system. It basically shuts you down. So you need to account for that. If something went down, it was offline. When I come back, I release the logs slowly. But that means the way that you send this log, where you store it, you need to be able to receive logs with delay and put them in the correct order, correct format. Right, so you think about this, otherwise you have all this log that timestamps basically they don't match. So, there are some of these tools also like it will help you for observability, Zipkin, Jacker, Jagger, Dapper, the different tools that you can use. We don't have any labs on those ones, unfortunately, but they're just overall basically that you can get some sort of like a trace like this. Basically tells you that when something is started through the end. Have you ever worked with the Ray? Anyone of you? Ray? So if you, there's a library called Ray for distributed training. And it has a part called like a Ray notebook. It's like it gives you a dashboard for, so just take a look at the website Ray. I think we also have a lab on it, but the website is pretty easy. If you, on top of your Jupyter, you do Ray, first import Ray, and on top of your Jupyter, if you do Ray init, it's like a Ray init. And inside this Ray init, I think if you put dashboard equal true, when it comes up, it basically brings up an API for you, like a IP endpoint accessible. Now, when you run your code within the array, within the Jupyter, it basically gives you pretty nice dashboard tracing and everything out of the box. So it provides technically these types of trace out of the box. You just need to be sure that you do Ray init on top of your Jupyter. For most of the functions, in order to give you this trace, you need to somehow decorate it with some Ray functionalities in order to basically trace it for you. But if you want something like that, that's also possible. Now, the next thing about the monitoring is that, well, we detect model decay, but the question is, okay, what is model decay, right? So we have talked about this. Model decay happens when your model performance over time, decay means like over time, basically goes down. Like maybe it was 95% accurate, now it's like a 90% accurate. Now, the types of decay, again, is kind of, could be like a static, there's like a between two time pace, and it could be like a drift, like it's kind of like a time based. Now, when the drift happens or model performance goes down, majority of time is because of the data. Okay, so you either have some sort of like a data drift, distribution of the data, customers are changing, types of customer, you have a new, you're targeting a new geography, or it's concept drift. That means concept has changed, word has changed. I don't know, this shoes is no longer a trend. So it's kind of like the concept, there's a change over there. It's also possible that like it could be some system failure, like you have sensor that you collect the data on, the sensor is bad, the data that you receive has a lower quality. That's possible. But that's also kind of, if you think about it, it's like a data based. So it's kind of like the data is causing. Now, when you think about the data drift or feature drift, this is just an example. If there's a shift in the distribution of the data over time. So when you hear this example, it's like you notice that like this month versus like next month, when you look at the distribution of the data, there's a shift. You have more like elderly, basically customers. So that's an idea of like a data is drifting. When it comes to the concept drift, and this one, like if you have a classification at this timestamp, then becomes this, then becomes this. This you see, there's the color is changing. That's the idea of like concept drift. An easy way for doing a concept drift in an unsupervised way is if you do, I think in the previous class we talked about this, kind of like you do some sort of like a class clustering. So if during training you do clustering and you have certain groups, and or during serving, let's say, actually during training, let's make an easy example. So let's say I have a data during training, and it's kind of look like this. It's just this really simple scenario. So when you do clustering and you found this cluster. Now, as time goes and you get new data comes through. As new data comes, you can add it. And then once in a while, you do reclustering. Now, one thing that you might notice all of a sudden is that there's a change in the cluster format. So all of a sudden now you get emerging concepts, emerging clusters. That is when the scenario, there's a concept is changing. You know, it's like you end up with a different types of labels, different types of clusters. All right, so, and this is again, if you do unsupervised, if you do supervised, that's could be something like you have a response and you see there's a change in the response. Then it's always important to, you want to be sure that you detect the drift on time. Always have some sort of like a boundary for when you do drift detection or when you do monitoring. If you monitor for accuracy, let's say, and you expect, let's say, reverse of the like, accuracy. So let's say this is the, if here is 100, like 100%, and you have here 90%, like your, like a red line. That if your model reaches 90%, you cannot serve it. So, and you have this 95% acceptable range. This is like it's something that you expect, like expected basically accuracy. So you serve the model, and then the model basically starts here, and over time you notice this model is like a accuracy is kind of like a going down. So if you leave this goes down, it basically becomes something like this, and the stop point actually becomes exponential. It just goes much faster. Now, what you could do is that if you are able to kind of like interpolate, I know the rate of decay, and I can estimate that this model will pass this point within, if this is time, within this many weeks. Right? So the idea here will be that if you can detect it ahead of time, you don't need to wait for here to retrain the model. Maybe at this point, you're like, okay, we know this is happening. So you already retrained the model. And at this point, you pull up the model here, and then this becomes the scenario. So by doing so, instead of letting a model fully breaks down and then just bring it out of the loop and build a new model, you constantly pulling up the same model by doing a small iteration. Why this is beneficial? Because, well, you kind of buying time for yourself. At some point, you can't do anything. This model will go here. Because as you go, then at some point you start here. But then it's not this month, maybe it's like a year after. Right, so it's kind of like by monitoring and kind of detection of when the drift is going to happen, you retrain, you have this pipeline that retrain the model, pulls the model up and continues. So I think that will kind of like summarize this model drift detection. But we monitor for the logs, and then you have series of ways that you can monitor. You can use series of libraries. TFDV is one of those. Scikit Multiflow, also another library for detection of this drift. Some of them they have dashboards, some of them they don't have dashboard. And if you are using Vertex AI in your project, when you build the deployment, if you notice that as part of your process setup, it is asking you for Vertex monitoring and drift detection. It's option over there. So if you're using Vertex AI and you're like, I don't want to build my own dashboard, out of the box is giving you that drift detection and schema validation, all of those. You just need to be sure that when you go to a setup, you actually select that. All right, so ways to mitigate the model decay. So this is technically one of the ways. But the question here is that what will happen if we detect this? So you have a pipeline, the pipeline basically detecting the drift, and something goes happening. What should you do? And there are a couple of questions that they always are being asked. Is like, well, if we detect drift, and the drift basically is root into some sort of like either concept drift or data drift. It depends which one of this is happening. Your decision of what to do next is also going to be different. So if you have a concept drift, we know that the concept drift means, well, probability of y given k y given x is different now, right? Because the label is kind of like it has changed. So if you have a concept drift, you actually have a much harder problem. Why? Because well, whatever label you have previously, you cannot use them anymore. If you think about it, when you have a concept drift, if you want to do retraining, that portion of the data that the drift is happening within is no longer useful. So you need to think of this. If this is happening, what should I do? Well, first thing is that if this is your data set, find which portion of this data, let's say this portion, the drift is related to, toss that out because, well, it's not useful anymore. Or maybe you can basically go over it and label it manually, but that's not useful. Then portion of the new data that you use to detect the drift, you can add it here to be a replacement for that part. That's the new data with the new label. If you have P of X is different or P of X given Y is different, the statistic of the data, the overall distribution of the data is different, then because the label hasn't changed, you don't need to get rid of the old data, right? So when it's kind of like actually, let me rephrase that. So when the statistics changes, you can look at the new data. Let's say during the training, you had customer age 18 to 30. Now, after a year, you have customer between age like 18 to 50. So you still can use the old data. But if you have seen the data set shift, that now your customer over the last year is all age 30 to 50, then probably the older, like age 18 to 30 is no longer useful. It's kind of like it depends on what is happening. But most of the time in this scenario, you still can use the same data and just add the new data to it. So that's around the data. Now, the next thing is, what about model? So I have a model that there was a drift and this model performance goes down. Should I toss out that model? Should I start a new model from scratch? Should I just continue retraining that model? What should happen? So that also depends on first types of model that you have. Certain models, they don't have a continual retraining. You need to start from scratch. Certain models that kind of like, they have continual retraining. So you basically can continue. Depending on where you are standing, if most of the cases like you can retrain the model. So when you retrain the model, let's say either of this has happened, and you want to retrain your model. That retrain means kind of like some sort of like a transfer learning. You are still using the knowledge from before, but you just want to do some updates. So that means from this region, that of the data, that the new data, you want your model to focus on that, to learn that. But something to keep in mind, you don't want your model to forget this part. If you keep only passing this to the model, all the weights adjusted toward this, it will forget this. So what you need to do is that to ensure that your model receives this, but certain percentage also from the previous data. To ensure the model does not forget about part of the data that comes from different categories or different distribution that you don't want the model to forget. But the part that you want the model to forget, it will automatically be updated because you give it a new data for that class. So that becomes like overall idea of like what you do. If you detect the drift, what should I do? That becomes something. Definitely be sure that communicate this wherever team that you are working, be sure that you have answer about like what happened, how much drift happened, communicate it. Having a drift is not a bad thing. So I know some engineers might feel like it's a bad thing. I'm going to hide it. I'm going to fix it myself. No, it's not about you. The drift happens. The world is changing. The data will change. The drift will happen. Actually, if you're working with me and you show that you detect drift, that's much stronger than you don't detect the drift, right? So if you detect the drift, that's really good. it's expected. It's expected the performance goes down, so it's good. Just, just be sure that you collect enough information and you just don't go and say that we have drift. You have information about how much drift we have, where is this drift, how we can address it and stuff like that. So just collect some information before doing that. Now, when it comes to model retraining, this retraining part, let's say there is a drift. There are different ways that you can do retraining. One is that, is on demand. So whenever there is a request, you basically do model retraining. On demand could be, you have a customer and you only retrain the model whenever a customer comes and says that, hey, I think I want you to update the model. Now the performance is not that acceptable, right? So you just wait for a request and then you do model update. That becomes on demand. Or you have a product team and comes says that, hey, we have lots of tickets, requests, so let's go update the model. You have on a schedule, you automatically have schedules. Every 3 months, we update the model. You have some idea, like you monitor it for a while, you have an idea, like every 2-3 months, we have a decay. So you're not waiting for that. You're kind of like a scheduling. Every 2 months, you have a model calibration. It could be availability of the new data. So you could also have a policy. Whenever we have this amount of new data and certain changes, maybe, this is total is your policy. Whenever we have this amount of data and this much changes, at least in the distribution or categories or something, we retrain the model. So if you think about it, when you build this pipeline, the monitoring pipeline is not only to monitor, it's to monitor, create an alert and an action, right? Alert will be the part that it lets you know, okay, hey, something doesn't work, I let you know. Over time, and when that alert becomes something that it reached to a threshold, becomes an action. That action, what it does, it starts another pipeline. It sends a request to another pipeline, says that, hey, we have this much data. And that request, again, could be time-based, could be on demand, and could be just simply based on how much data or changes you have. So, model performance degradation goes down. Data drift detection is all like a reason could be for you to create this. And again, you could have some other custom ways of detection at drift because not all applications have everything like this ready. So anyway, so whenever you basically work on your data pre-processing, when you have some sort of like a drift, remember that you might have done lots of pre-processing and basically pipeline creation, but you might need to rethink it, to redo it. Because when the drift happens, some sort of drift, whatever you have done doesn't necessarily mean it will work now. Okay, so that's something to keep in mind. And again, you may also need to totally restart the model because what you notice is that because amount of drift was really high, retraining of the model doesn't make sense. So you basically need to start from scratch. And that comes back from what we have said from the beginning of this class. It's kind of like a loop. It's really possible that you go all the way back to re-scope and regenerate everything, or you could go somewhere in between in the pipeline, like maybe from just data transformation or just from model calibration. All right. All right, I'm going to stop on this one and let me see. Yeah, I'm going to stop on this one.